Well, hey there, welcome back. This is a video tutorial that's specifically dealing with the two sample t-test. Up until this point, we've used single sample techniques, but most research involves the comparison of two or more sets of data. And this data sometimes comes from two completely separate groups, or it may come from the same group of participants, and data is collected before an intervention and then after an intervention. A research design that uses a separate group of participants for each treatment condition is called an independent measures research design or a between subjects design. However, a research design that uses two sets of data obtained from the same group of participants is called a repeated measures design or a within subjects design. What we're going to focus on in this video tutorial is an independent measures research design or a between subjects design. And when a researcher has that type of design within a research context, they will most likely employ a two sample t-test. Throughout this tutorial, I will show you how to calculate a two sample t-test to assess significant differences between samples. So in order to calculate a two sample t-test statistic, there are a series of steps that you should keep in mind. Now I'm going to lay these out as three separate steps, but there is some alternative formulas that you can utilize to calculate some of these steps. I'm laying it out in a three-step way for people that desire simplicity and are simply looking to get to their t calculated as quickly as possible, no matter how the samples may vary in terms of sample size. So I'll start with the first step. The first step will involve you calculating a pooled variance. Recall that the abbreviation that we've been using for variance is a lowercase s with the exponent of 2. And all we're doing here is just throwing a subscript of p on it because it will represent pooled variance. Now the formula for pooled variance is the sum of squares 1 plus the sum of squares 2 in the numerator over the degree of freedom 1 plus the degree of freedom 2 in the denominator. So variance is the average squared distance that scores are away from the mean. And you see here, essentially what we're doing is we're taking the sum of squares for sample 1 and we're pooling it together with the sum of squares for sample 2. And ultimately, to get our variance, we need to divide the sum of squares by our degrees of freedom. And in the denominator, all we're doing is pooling together those degrees of freedom so that we can get a total variance for both of the samples that we'll be utilizing. So these numbers that are listed here are just subscripts and they are meant to differentiate one sample from the other. This is a two sample t-test related statistic. So we're working with two samples and one basically represents sample 1 and 2 represents sample 2. All right. So the second step that you'll need to calculate is the standard error of the mean difference. And this is how it's represented in abbreviation form. We have a lowercase s, which represents the standard deviation. Then in subscript format, in parentheses, we have the sample mean 2 taken from the sample mean 1. So given that ultimately these two sample means are being drawn from two larger populations, we should expect that there is going to be some slight differences between the sample means and the population parameters that they expect. So if we expect there to be mean differences across parameters and statistics, we should also expect there to be average distance differences that exist when we subtract one mean from the other and compare it to what it would be like if one population mean was subtracted from the other. So this is getting that the average mean difference that should be expected across these samples. The formula that I want you to utilize for calculating this particular statistic is this. So in the numerators, we have pooled variance from step 1. In the denominator, we have the sample size for each respective sample. And we're going to take the square root of everything. So essentially what you will do is drag the pooled variance from there into these respective numerators so that you can calculate your standard error for the sample mean difference. Do not look at this as being a formula. Okay, it's just simply an abbreviation that represents the standard error for the sample mean difference. Step 3 will involve you actually calculating your t. And it'd be a good habit to just call this t calculated in addition to describing the statistic based on whatever research design you have. So it's still a two-sample t-test statistic, but it's a good practice to call this t-calculated so that you won't confuse it with the t-critical, which is found in step 2 of hypothesis testing. Okay, the formula for this two-sample t-test is mean 1 minus mean 2 over standard error for the sample mean difference. So essentially what you will do is take step 2 and drag it on down here into your denominator for your t statistic. So with that being said, let's work through an example so that you can put feet to this and be able to calculate any kind of problems I give you in class or through homework assignments. So, for example, let's say that a researcher was interested in assessing significant mean differences in sharing between lower class individuals and upper class individuals. When we talk about lower class individuals and upper class individuals, specifically what we're talking about is socioeconomic status. So individuals that may be living below the poverty line and individuals that may be living well above middle class. Let's say we had this data. Let me write this out. Lower class, and we had upper class. And let's say for the lower class, we had n equals 12 individuals that we sampled who shared on average 5.2 times a week, shared some type of item with the sum of squares of 11.91. And let's say for upper class individuals, the sample characteristics were mean of sharing of 4.3 with a sample size of 12, a sum of squares of 9.21. And what we're looking to do is assess if there's a significant mean difference across these different classifications. Now, in a cursory way, we can see that 5.2 is obviously higher than 4.3, but we'll be trying to make a determination to see if the significant difference is really due to classification or if it's more or less related to sampling error and differences that may exist when you pull the sample information from larger populations. So we'll start off by first distinguishing these two samples with the subscript. What I typically do is I'll select the mean that is the highest and label that as sample 1, and I'll label it as sample 1 by putting a subscript of 1 simply below all of the statistical information that pertains to it. This is sample 1. Then we come over to the upper class portion and we will label that sample 2 with the subscript of 2. Once we've done that, we can jump right into our formulas here. So our first formula involves taking the sum of squares for 1 and 2 and pooling that and ultimately dividing by the total degrees of freedom. So we have 11.91 plus 9.21 over 11 plus 11. Once we do that, we end up with 22 in the denominator, 21.12 in the numerator. Once we do that out, we end up with 0.96 in terms of our pooled variance. Step 2 involves calculating our estimated standard error of the mean difference. So I'm going to take that pooled variance and simply bring it down and put it in the formula. This time I'm not going to write out the formula. Be careful in the denominator to insert your sample size and not your degree of freedom. And remember, this formula for the standard error of the mean difference involves taking the square root of everything. So I'm essentially dragging step 1 down, and then I'm grabbing my sample sizes down and putting those in the denominator. So once we do out those fractions, we end up with 0.08 plus 0.08. We're going to take the square root of all of that, and then that equals to 0.16. And then when we take the square root of 0.16, we end up with 0.4 as our standard error of the mean difference. So on average, that's the mean difference that we should expect when we pull two different samples from two different populations and subtract one from the other. Finally, we do our calculated t. And this is the calculated t for the two sample t-test. And we have 5.2 minus 4.3 over 0.4. Once we do that out, we end up with 0.9 in the numerator, 0.4 in the denominator. We do that out, we end up with a calculated t of 2.25. And that's it. Those are the 3 steps that you can follow. Now, I was telling you guys earlier that there is an alternative formula to get your estimated standard error of the mean difference, but that formula is best to be used only when you have sample sizes that are of equal size. When you have variation that shows up, then you shouldn't utilize that formula, but rather you should pool your variances first and then go the route of calculating your estimated standard error of the mean difference. Now, we have a t calculated, and we still need to make a decision in regard to rejecting or accepting a null hypothesis. In order to do that, we must go back to our t-distribution table, locate that t-critical, and then use that t-critical as a gauge of whether or not this mean difference is significantly different from what's to be expected, or if it's actually what should be expected. So let's go to our t-distribution table now. So when we go to our t-distribution table, we will be bringing over 3 pieces of information. We'll be bringing over the alpha level, the notion of whether or not it's a one-tailed test or a two-tailed test, and we'll also be bringing over our total degree of freedom. Now, I didn't mention this earlier, but let's say that we're just looking to see if there is a significant difference between lower class individuals and upper class individuals, and we are not specifying a direction in terms of where we'll see that difference. So in that case, we will be going with the two-tailed test, and let's say we're going with alpha 0.05. So we'll be going with alpha 0.05. It's a two-tailed test, and we will go down the alpha 0.05 two-tailed test column until it intersects with the correct degree of freedom that is related to our study. Now, our degree of freedom is 22. So if we zoom in, we will find that our T critical for this study is 2.074. And specifically, it's plus or minus 2.074 because we will be open to significant differences being above the mean difference to be expected with the parameters or possibly below it. Let's go back to the live board. So our T critical is plus or minus 2.074. Now, this is a simplified version because now the graph is much more complicated now, folks, because we're dealing with two different samples and the difference of the means. But I'm going to simplify it just by drawing out one normal curve here. All right, so based on this being a two-tailed test, alpha 0.05, and the total degree of freedom being 22, our T critical is 2.074 on this end and minus 2.074 on this end. Okay, we have a T calculated of 2.25, which will likely fall if this was a number line, that plus 2.25 will likely fall within this region, and these are regions of rejecting the null, and this is a region of acceptance. Okay, so with that said, what will we do in terms of rejecting and accepting a null as it relates to this study? If you said reject the null, you are correct. If you said accept the research hypothesis, you are correct. Okay. So we're basically doing that because our T calculated is out in the tails. The apple is falling far from the tree, right? And it is significantly different, not just by chance, but perhaps because of the manipulation of the socioeconomic classification. Now, just to take this a step further, okay? Sometimes a question will ask you to calculate the effect size, and one of the most frequently used effect sizes is R squared. And effect size deals with determining if the independent variable is significantly impacting the dependent variable independent of sample size. So sometimes significant differences can occur just based on the sample size resembling the population size, and this R squared gets around that by specifically focusing on the T that's calculated and trying to remove the influence of the sample sizes. When you calculate R squared, you should end up with a decimal, and when you convert that decimal into a whole number, that whole number will tell you the percentage of variance that is explained by the independent variable. This T here is going to come from the T that you calculated. Okay, so essentially what you would do is you would take 2.25 and square that, put that over 2.25 squared plus the degree of freedom for one sample, which is 11. Okay, so in real time, folks, I'm going to do this out. So when we take 2.25 and we square it, we end up with 5.06. And that means we have 5.06 in the denominator. Take 5.06 and we add 11 to it. We end up with 16.06, 5.06, and then when we divide 5.06 by 16.06, we end up with 0.32. We convert that to a whole number, we end up with 32%. So this is telling us that classification in terms of lower class and upper class is accounting for 32% of the variance or the difference that is occurring in terms of these individuals sharing. So with that being said, I hope that this video tutorial was helpful. Feel free to rewind it back. Let me know in the comments below if it was helpful and some additional instruction or tutorial videos you would like to see moving forward. Take care.